In traditional physics, much of our understanding stems from isolating fundamental variables like mass, force, velocity, and charge. This reductionist approach has allowed us to explore and explain a wide range of phenomena in the universe. However, when it comes to understanding complex, emergent behaviors, those that arise from the interaction of many components, this approach often falls short. Triadic physics introduces a new lens for interpreting physical reality. Rather than treating variables in isolation, this framework looks at triads, sets of three interrelated variables whose interactions give rise to emergent properties. These properties, crucially, are not present in any single component of the system, but emerge logically from their interrelationship. Consider, for instance, the concept of temperature. A single particle on its own cannot possess a temperature. Temperature arises only when we examine the collective behavior of particles in a system. In the triadic framework, temperature is understood as the result of the interplay between kinetic energy, particle mass, and volume. It is the interaction between these three variables that leads to the emergent property we identify as temperature. This principle, the emergence of new properties through interaction, lies at the heart of triadic physics. By shifting the focus away from individual variables and onto the relationships between them, this framework enables a more intuitive grasp of complex systems. It explains not just how isolated forces or quantities behave, but how their combination leads to higher-order phenomena. This shift in thinking represents a departure from the traditional reductionist view. Instead of assuming every phenomenon can be traced back to a single, isolated cause, triadic physics reveals how interdependence among variables leads to emergent realities. By identifying the right triads, we gain a deeper, more holistic understanding of how the universe operates across both fundamental and emergent levels. Through this lens, classical physical laws governing pressure, energy, or voltage can be reinterpreted as emergent attributes. These attributes arise from the logical relationships between interconnected variables. Rather than replacing traditional physics, triadic physics complements it, offering a more cohesive way to comprehend the behavior of natural systems, particularly those with inherent complexity. In this framework, the universe is not merely a sum of parts, but a tapestry of relationships. It is through the interactions within these systems that the emergent properties we observe are brought into being. Let's return to temperature as our first example of how triadic physics operates. In this framework, we see temperature emerging from the interaction of three key variables. Kinetic energy, A. This represents the energy associated with the motion of particles. Faster-moving particles have higher kinetic energy. Particle mass, B. The mass of each particle determines how kinetic energy translates into motion. Heavier particles store and transfer energy differently than lighter ones, volume C. The volume of the space in which these particles move defines the limits of their motion and how energy is distributed across the system. In this view, temperature is not inherent in any of these variables alone. It emerges from the way kinetic energy, mass, and volume interact. Kinetic energy drives the particle motion, but the mass of the particles affects how this motion expresses itself. Heavier particles may move more slowly at the same energy level compared to lighter ones, affecting how energy spreads across the system. Volume, meanwhile, moderates how closely particles can interact, influencing how their kinetic energy is distributed. The balance between energy input, particle characteristics, and available space culminates in the emergent property we recognize as temperature. Rather than treating temperature as a basic, standalone property, triadic physics reveals it to be a manifestation of deeper relationships. This way of thinking can be extended beyond temperature, opening new pathways for understanding other physical phenomena. We can apply the same triadic reasoning to another familiar concept, pressure. Traditionally, pressure is seen as the force applied over a surface area. In triadic physics, we can explore the emergence of pressure through three interconnected variables: force, area, and particle velocity. Force, A. Particles exert force when they collide with the walls of a container or with each other. This force is a result of their kinetic energy and velocity. Area, B. the surface area over which the force is distributed. A larger area spreads the force out, reducing pressure. A smaller area concentrates it. Particle velocity, c. The speed at which particles move directly influences the magnitude of the force exerted during collisions. Faster moving particles collide more frequently and with greater intensity. Pressure emerges from the way these variables influence one another. The force applied by the particles is driven by their velocity. The faster they move, the more forceful their collisions. However, the distribution of this force across a given area modulates the resulting pressure. A smaller area means the same force is concentrated, leading to higher pressure, while a larger area diffuses the impact. Thus, pressure is not just the force or the area alone, but the result of the dynamic interplay between the intensity of the collisions, force and velocity, and the space available for these collisions to occur, area. The emergent property of pressure arises from this continuous negotiation between energy, motion, and space. Now let's look at how triadic physics can reshape our understanding of electromagnetic phenomena. Consider the variables often examined separately in traditional electromagnetism: voltage, current, and resistance. We can view these through a triadic lens. Electric charge, A. Charge is the basic property of particles that defines their interaction within an electric field. The amount of charge determines the intensity of electrical forces. Current, B. This refers to the flow or movement of electric charge. A higher charge density or a greater rate of flow results in a stronger current. Resistance, C. Resistance opposes the flow of current, regulating how easily charges can move through a medium. It can be thought of as a moderating factor that influences the efficiency of charge transfer. Voltage emerges from the complex interaction of these three factors. Electric charge is the driving force, creating potential differences that push charges to move. The current reflects the flow of these charges, and resistance governs how easily this flow occurs within a system. Resistance limits how quickly charges can move, shaping the current and determining how much potential energy, voltage, is required to sustain the flow. Thus, voltage is not a standalone property but an emergent phenomenon that arises from the tension between the amount of charge, the movement of that charge, and the opposition to that movement. The balance between charge flow and resistance produces the voltage observed in the system. Finally, let's apply triadic physics to thermodynamics. Thermodynamic energy, particularly free energy, can be understood through a triadic model that incorporates time-dependent interactions. Heat, A. Heat is the total kinetic energy transferred between systems or particles. It represents the energy that is in transit. Entropy, B. Entropy measures disorder in a system, indicating how energy is distributed and how likely it is to flow in a certain direction. Higher entropy suggests a more even distribution of energy, while lower entropy implies concentration. Time, C. Time allows these processes to unfold, giving the system the opportunity to evolve from one state to another. Without time, energy transfers and entropy changes cannot fully manifest. Free energy emerges as a balance of these three factors. Heat represents the kinetic energy driving the system's transformations, while entropy regulates how that energy is organized within the system. Over time, these interactions determine how much of the heat can be converted into useful work or how much is lost to disorder. Therefore, free energy is an emergent property that depends on the flow of heat, the system's entropy level, and the evolution of these processes over time. It is not a fixed property, but one that arises from the ongoing dynamics of energy transfer and entropy change in relation to time. At its core, triadic physics moves us beyond a fragmented view of isolated variables and instead encourages a systemic approach. In this model, three interdependent variables combine to produce emergent properties. These emergent properties cannot be reduced to any one of the variables. They arise from the balance and interactions within the system. The focus shifts from analyzing individual forces or quantities to understanding how relationships between variables lead to new, higher-level properties. This approach applies not only to phenomena like temperature or pressure, but to a wide range of physical systems. It opens the door to reinterpret even the most fundamental phenomena as emergent from triadic interactions. What makes triadic physics so powerful is its ability to simplify complex phenomena into a cohesive and logical framework. By identifying the correct triads, we can logically explain how new properties emerge, offering a clearer, more unified perspective on the world around us. Nature, in this view, is not a collection of disconnected parts, but a system of relationships where meaning and behavior arise from interaction. In essence, triadic physics invites us to see the universe as a web of interdependence, where every significant property emerges from the intricate balance between variables, revealing a deeper and more connected understanding of reality.